we have a corollary from the intermediate value theorem. So if f is a function mapping this interval to R, I suppose that f is continuous. If f of a and f of b, if f of a and f of b differ in sign, if f of a and f of b differ in sign, that means maybe f of a is positive and f of b is negative, or the other way around. F of b is positive, f of a is negative. If they differ in sign, then their product will be negative. That implies that there exists a c in this interval such that f of c is equal to 0. In simple terms, this function will be having a root between the interval. We'll be having a root within the interval ab. If at all the product of f of a and f of b is negative, then there exists a root of the function which is c in that interval such that f of c is 0. So the proof of this follows the intermediate value theorem, which we have just proved in the previous session. So we want to look at the fixed point theorem, but we are going to use this important corollary from the intermediate value theorem. So the fixed point theorem, for it, what it states is that if our function f is mapping this interval to that interval, is taking the image and the object, they are kind of similar. If they are similar, then there exists a c in the interval 0, 1, such that f of c is equal to c. It's like now c is a fixed point. C is not changing. Yeah. F of c will be c. It's a fixed point in that sense. So how can we prove this? We are going to prove this by contradiction. The fixed point theorem. Proof. Suppose that we want to show that there exists a c in here such that f of c is not, such that f of c is c, such that f of c is c. So suppose that there exists a c in this interval such that f of c is not c. Suppose that f of c is not c. In particular, we are going to take a specific example. Suppose that I'm going to say that suppose, because I want to prove this by contradiction, suppose that we have no c in that interval such that that relation is satisfied. Let me use this. Suppose that there exists no c in this interval such that f of c is equal to c. So this implies that this implies that if we have no c such that this relation is satisfied, this implies that for all c in this interval, for all c in that interval, comma, f of c is not equal to c. In particular, f of 0 is not equal to 0, f of 1 is not equal to 1, is not equal to 1. Then we are going to define a function hx, which is f of x minus x, then h is continuous. H is continuous. Why is h continuous? H is continuous since H is a difference, since H is a difference of two continuous functions. F of x is continuous by definition. Also, f x, the function x is continuous. So h is also continuous, being a difference of two continuous functions. Being a difference of two continuous functions. Then h is continuous. Also h of 0 is equal to, I'm going to substitute here, h of 0 is equal to f of 0 minus 0, which is equal to f of 0, and h of 1 is equal to f of 1 minus 1 minus 1. It's just simply f of 1 minus 1. Now, what do we observe about h of 0 and h of 1? H of 0 is f of 0. Remember, this function here is taking this interval to this interval. F maps 0, 1 to 0, 1. It's like the image of this interval is consisting of things which are positive. It's consisting of things which are positive. Now, also f of 0, the image of 0, since it is not 0, the image of 0 will also be in this interval. So since it is in here, then it is positive. So that implies that, now h of 0 is positive. It's greater than 0. It's positive. Then h of 1, what do we observe about h of 1? H of 1, remember f of 1 is the image of 1. It's the image of 1, so f of 1 is in this interval 0, 1. F of 1 lies in here. F of 1 lies in here. So that means f of 1 can be 0, 0.1 up to 0.9, up to 0.9. That is what? That is f of 1. So if f of 1 is taking these values, if you pick any arbitrary value minus 1, we shall get something which is positive, which is negative, sorry. We shall get something which is negative. If f of 1 lies within this interval. So this is less than 0, implying that h of 1 is negative. So h of 0 times h of 1 times h of 1 is negative. It's negative. Then by our important corollary, this implies that there exists a c in 0, 1. By this important corollary, we have a c in 0, 1 such that h of c is equal to 0. Such that h of c is equal to 0. What does that imply? Now, if h of c is 0, then let us compute h of c. H of c is equal to f of c minus c, and this is equal to 0. So we have f of c equal to 0. So we have our result. The fixed point theory. So generally, what can we conclude? So generally, if f maps the interval FB to the interval FB, and F continuous maps the interval FB to the interval FB and F continuous. Then there exists a D in the interval FB such that F of D is equal to D. Then you can have that. You can consider the general case for this result, and also the proof of this follows the same argument. So we are going to look at other types of connectedness in the next session.